We have somewhere around 6 to 8 closed loop liquid coolers deployed around the office, mostly for test benches and things like that. And some of these have been in use for several years at this point, most of them since the Kraken X62 launch. So doing some regular maintenance and cleaning, we noticed that they needed to be cleared of dust. And that presented as an excellent opportunity to do a dust benchmark for a clogged radiator. One of these coolers had a few years of dust, and this particular one was in use back when we were still at the house. So that'll include a lot of cat hair from Snowflake the cat, seen here inspecting some components. We became curious as to the thermal impact of a realistic accumulation of dust, so we applied our exhaustive CPU cooler test methodology to it for a highly controlled A/B look at a dusty radiator versus a clean radiator. Before that, this video is brought to you by MSI and the Z490 UniFi ITX motherboard for Intel 10 series CPUs. The MSI Z490 UniFi ITX board benefits from a memory layout that makes memory overclocking easy, positioning the board well for enthusiasts who want to tinker on a bench or in an ITX system. The MSI Z490 UniFi runs 90 amp power stages, a 10-layer PCB, and seats the memory as close to the socket as possible, all of which benefit the overclocking experience. Learn more at the link in the description below. Although we're testing a CPU cooler today, the same sense of scale can be applied to a case, a GPU cooler, anything else that accumulates dust. We've got a couple of different units we're testing. So one of them is a Kraken X62 as stated. That's being tested for CPU thermals, and that one's not really too bad. It was getting to the point of being bad, but not there yet. It wasn't completely jammed up, just kind of gross. This one is a really old cooler that we have, and it's, not even sure what it's been used in at this point, but this is what we'd call very bad. So this is gonna be one that we're using for an impedance test on technically a wind tunnel. It's like a flow chamber or a flow tester if you prefer, but basically we're gonna mount this to the flow tester, get a fan on it, we'll test it clean versus dirty. We're doing the same for the X62 at 280 mil CLC. That one's gonna be for thermal testing. This one will be for flow testing. And the end result is that we'll be able to generate some CFM numbers, some LFM numbers, thermals, RPM changes as well when you change the resistance that the fan is facing. And then after all the charts, we're gonna walk through some of this testing equipment in the testing room, just like we did the other day for the graphite thermal pad testing, to show you some of the basics of how this deployment works and why we think it's a great solution for testing things like this. This should be a fun test because dust is a real problem that people face with their PC builds. Obviously, you should clean it regularly, but if you've ever wondered how much does it really matter, that's what we're looking at today. One thing we're really not looking forward to, and by we, I mean whoever is standing behind the camera when we have to film it, is cleaning out the radiator and getting all of the dust out of it. So that'll be a fun slow-mo shot. But otherwise, let's get into the charts and we'll go through the testing room after that to talk about this setup. We'll show some of this testing equipment after all the charts, and it'll be timestamped below as well. But we're going to start with fan LPM and CFM changes. This test uses a flow tester and hot wire anemometer to measure performance of a fan, tested with both a dusty and a clean 140 mil radiator that mounts flush with the tunnel. We used the same NZXT Kraken X63 radiator fan for all of these tests, and that's NZXT's recently improved fan. The radiator and the fan were always mounted in the same orientation and always at 100% fan speed. The dusty radiator resulted in an FPM of 240. We'll look at CFM in a moment. And that compares to a clean radiator average of 381 FPM. This is measured in linear feet per minute, called FPM or LPM interchangeably, and as you'd expect, is a linear measurement. That's an improvement of roughly 58.8% linear feet per minute flow. Now, of course, this won't translate to a linear temperature improvement, especially since temperature is reported on an arbitrary scale, but we'll get into the temperature changes momentarily with an X62. More flow will correspond with thermal improvement. Ultimately, it's just a matter of how much translates to real world. If we remove the radiator, our baseline flow with just the fan is about 517 FPM. Interestingly, the radiator acts as a flow straightener. You can see that the two radiator lines are much flatter, while the unencumbered fan has more variable flow patterns. Even still, it's a range of about 10 to 15 FPM at most. Keep in mind that 100% speed will have slightly different RPM based upon resistance, which we'll look at momentarily. A lot of people like to use CFM numbers to compare fans against one another on retail sites like Newegg, but most of the time, these are not directly comparable between fan manufacturers. CFM is measured different ways, and so isn't a linear comparison cross-brand. You can often compare intra-brand for CFM numbers like Noctua against Noctua, NZXT against NZXT, but comparing between two brands is often not something that really works. Our testing is conducted the same way for every single fan, so we can do cross-brand or cross-test comparisons. CFM is a measure of cubic feet per minute flow, which is a calculation involving FPM, already reported, against a known area of a flow chamber. Because we know the area of the chamber, we can calculate this with just FPM. The end result is a CFM of 43 for the dusty radiator, 68.6 CFM for the clean radiator, and 93 for the unhindered fan. This is linear with FPM and has the same percentage scaling, so the dust test means that the fan achieves 46% of its total possible unhindered performance. The clean test achieves 73.8%, and 93 CFM would be 100% baseline. Keep in mind that this will change with different radiators, obviously, particularly thicker ones or ones with different amounts of dust. We didn't chart this point, but just as a note, in this particular test, we found an RPM of about 1800 to 1806 with the dusty radiator, about 1820 to 1823 with the clean radiator, and about 1827 without any radiator at all, as measured with a laser tachometer. Our next set of tests will move to a less disgustingly dusty radiator, our X62, rather than this particularly gross 140 mil radiator. The X62 is less dusty, so the change won't be as extreme, but it's still pretty bad and probably representative of what a lot of people are using. One of the more minor but interesting impacts to cooler performance from dust blockage is the change of fan speed. This factor is easily overlooked because it isn't the temperature column in the data, obviously, but an auxiliary variable that can influence the results beyond strictly dust thermals. That said, in a realistic environment, most people aren't going to change their RPM to be lower after cleaning out the system. So there is some reasoning for testing both an RPM-controlled setup and one which follows the behaviors and characteristics of dust blockages. Here's an overtime plot of the fan RPMs with the system configured to our 35 dBA noise-normalized level, as tested at 20 inches distance and in a noise floor of 26 dB. That happens to be about 38% fan speed for these two fans on this cooler. This is back on the 280 mil radiator and on the test bench rather than the tunnel, so we're looking at data from our standardized test bench now. We have intentionally zoomed this chart scale to help visualize the relatively minor difference. Averaged for both fans and across multiple runs for each test configuration, we see the clean radiator's fans, and it's the same two fans, mind you, test at about 2.6% higher RPM. We're at around 715 to 718 RPM rather than 697 to 701 RPM with the original testing data for the dusty radiator. The impedance to airflow is creating enough resistance that the blades aren't spinning quite as fast, which also reduces air through the radiator, but it's not a huge difference. Because the fans have a wall to push past, RPM will often drop from the impedance. We see the same in case testing, where removing the most obstructive case panels will cause an increase in fan RPM by way of reducing the resistance to airflow. This test looks at performance on our 3950X test bench with a 200 watt heat load using our standard testing methodology of rendering an image for 23 minutes with Blender and averaging against steady state. You can watch our cooler reviews or cooler methodology content piece linked in the description below for more information on how we conduct this testing in a standardized and replicable way. Rather than bar graphs against the other coolers, we're focusing on an overtime graph for this A/B test. In this one, with this particular cooler and test setup, we end up with this chart. The clean test plots at about 48 degrees Celsius delta T over ambient throughout the test, with idle around 10.8 degrees over ambient. The exact same cooler, except before cleaning the dust, plotted at around 50.8 degrees over ambient once steady state was achieved. Note that this is the average of 4 or more runs each, and the pump speed was 100% for this testing, so about 2600 to 2667 RPM. We're seeing a maximum average steady state difference of about 2 to 3 degrees Celsius at 100% fan speeds. We next tested with our 35 dBA noise-normalized configuration, so about 38% PWM with this setup. But we made one change that exits our standard testing methodology. For this one, we also dropped the pump speed to about 2000 RPM from about 2600 plus previously. In theory, this will exaggerate the heat difference and represent a still quieter configuration. With this setup, the clean radiator ran at about 56 to 57 degrees over ambient, while the dusty one climbed to about 61 degrees. We're seeing a maximum delta of about 3 to 4 degrees with the same radiator tested in clean and dirty states. Obviously, dust is variable, and the amount you have will change. That couple degrees can account for maybe a few megahertz on an AMD CPU. for what it's worth, but it's also just a good idea to clean it before it escalates and starts causing other damage. And of course, it may give you that extra headroom needed to push an overclock slightly higher. So this is the fan testing and flow testing area, but we've got a couple of pieces of equipment for this. One of them is a custom PCB that isn't used in this testing today, but will be used in future fan testing as we get to it. We've had the setup kind of complete for a couple of years now, but it's always been missing one piece or another, and also time was a problem. So we finally deployed it. To go over some of the really basics as quickly as I can, this is the flow tester. It's a known area, known volume, and we mount the fan and the radiator to this side. Right now it's just the fan. The last numbers I ran were for an unobstructed fan with no radiator, but we also did testing with this, which is just absolutely beautiful. So that was on, that monstrosity was also on there. And then we have the fan mounted in a push configuration, not pull. And that's what we did for the dust obstructed numbers. To mount it, we've got some holes in here. There's a swappable plate. There's another piece we can use for 120s. So we can do 120 or 140 on this. We can't do anything larger than that. We could make more plates for smaller ones, although it starts to get a bit awkward, but works really well for 140s. And these are for guidance. It helps with getting more accurate numbers at the end of this. So the anemometer is extremely sensitive. Most of them are. The wire we'll have to get a close-up of because it's going to require a very tight zoom. But there's an extremely tiny wire in there that is, I don't really have a point of comparison for how small it is, but it's about the size of a piece of dust, except not one from that radiator. There's also a thermocouple above it just for ambient temperature, and this is set up to read what's coming through, so that's what gives us our number in linear feet per minute flow. The mounting solution, biggest problem with this thing is it needs to be in precisely the same spot every single time. If you have it, we actually had another one that was mounted here previously. So if you had this here or here or here, it'd be a different number. So all that really matters is it's the same spot every time. So Andrew designed this in Blender, which we use for benchmarks often, but this was 3D printed, and we have a detachable bracket for the anemometer. Let me cover it up to protect it first. So there's the bracket, just 2 screws on that side, nut and bolt solution, and secures it. We've got tape in there just as a shim, and that's what holds it in place for testing. So that mounts here. That was our 3D printed solution. The fan speeds are taken with a laser tachometer. We can also take measurements in a more advanced way that I'll show in a moment. But just for a quick, simple measurement, we use the laser tack and some shiny stickers. So you can get kind of, like you can see, I'm getting it's assuming a circular fan, so we're getting like a 500 RPM reading. So that's what I use to validate the speeds. The fan itself is plugged into this simple PCB where we've got 12 volt, 5 volt, or sorry, 12 volt, 7 volt, 7.2, 9 volt, all that stuff, and then Molex. So that powers us. We're just at 100% fixed speed at this point with that setup. Same Silverstone SFX power supply that was powering our dummy heater fans, and the fan's on now. A couple of notes here. This is not as controlled a test environment as we do for the actual testing, so several things I make sure of are the status of the door to the room, the status of the air conditioning, all of that stuff's really important. Air conditioning especially affects the test. I also don't position this or anything else anywhere near the exit to the tunnel. Normally we have it all out of the way so there's no obstruction. Same for over here. There's normally nothing anywhere close to the fan, but we're just doing a demo for filming here. So I've just unobstructed the anemometer, and now it's going to start taking a linear feet per minute reading. So that's what that number is. We have the room ambient temperature as well, and that's the basics of how this works. A couple of other points. We also have this setup where this is a really tiny oscilloscope, and we've got that wired into a custom PCB. So this can do 2 fans, positive, negative terminal, all that stuff. Hooks into the oscilloscope. This plugs into a laptop, and then we can use software to take or set fan RPM. So this is all just custom made, and we worked with an engineer in the industry to help get this stuff done. So this allows us to do direct fan RPM control, whereas the other PCB is a simpler 100% or whatever percent setting based on the voltage. So there's a lot more to it than that, as always, but we're just trying to cram it into this video as part of the first deployment in an official capacity of the wind tunnel. It's not really a wind tunnel, but That's what we've been calling it. So flow chamber. So that's the first official deployment. We'll probably do some kind of more in-depth testing methodology piece in the future once we get into fans, and well, it'll really just be fans and fans versus radiators. But that starts us off with a feature test on dust. So now that you've seen the basics of how this works, we can jump back over to the main set for the conclusion. Okay, so that's it. So basically, the 280mm CLC wasn't quite jammed enough to really create huge issues. First of all, being a larger closed loop liquid cooler that's actually pretty good does help it out because it's in a better starting position than, say, this one, or maybe a Hyper 212 or something like that that's jammed with dust, because there's a lot more surface area to work with even when it's pretty dusty. So that's beneficial here. We were starting to see upwards of 4 degrees difference with the lower fan speed and quieter testing on the X62, and that would get worse as you get into a lower quality of cooler. So that's something to keep in mind. Obviously, the end conclusion here is just clean your computer. That should have been clear from the start. But if you're wondering how much it really matters, well, what we'd call a medium accumulation of dust is not completely terrible. It's once you start getting to this level that it really matter. So with this, we didn't do the thermal testing, but we did do testing with airflow. And in that instance, we were seeing a difference of about 58% or so for a clean versus a jammed radiator in terms of the linear feet per minute flow or the CFM flow. So pretty crazy difference. And you're just, at this point, if the fan's on this side, you're just blowing into a wall. So makes sense that it'd be pretty poor for performance. If you're getting to this point, you're not really sure how to clean your PC, well, the basics, pretty straightforward. If you have dust filters on your case or you have ultrafine mesh, probably most of the dust is accumulated to that. We actually, in the process of looking for other radiators in the office that were jammed up, we looked at some of our oldest production machines, and they were really not bad. So it was the case that was bad, where the case filter did its job and it was destroyed with dust. And that will impede flow, it will increase thermals, but we didn't have jammed up radiators because the case dust filters were catching it, and then the case front panels where they have that finer mesh, those were catching it too. So it wasn't too bad there. To clean the dust filters on cases, one of the best things to do is just pull it off if you can and run it under the sink and then just lean it on a wall to dry for a little bit. That's the quickest way to clear it out. If it's a component where you can't really easily get it under the sink or underwater, then you could always just use compressed air. Downside there is that if you leave it in the case, while you're doing that, you're just kind of blowing the air around in the case. So maybe take it outside or something like that. Vacuums are something a lot of people use. You do need to be careful with them. Vacuums are an extremely high potential of carrying static electricity. Electrostatic discharge is a real thing that can definitely kill components, especially when you have that level of charge. So just be careful with that. Don't shove a vacuum cleaner nozzle into your memory or something sensitive. And if you're going to use a vacuum, maybe just stick to the filters in the front of the case. Use compressed air for the rest, just to be safe. But that's really all there is to it. The conclusion is clean your damn computer. But thermals, not nearly as bad as we were expecting for the medium jam. This one, though, airflow differences for jammed versus not with this level of dust was pretty crazy. So that's it for this one. Thanks for watching. Thanks for supporting this type of content where we get to use some unique testing utilities that you don't see a whole lot of on YouTube, at least. And as always, you can support this type of effort by going to store.gamersnexus.net to pick up a shirt like this one of our mod mats if you want something functional, one of our mouse mats in the wireframe variety if you want something functional there, or any of the other items on the store. Or you can go to patreon.com/gamersnexus to help us out that way as well. Thanks for watching. Subscribe for more. We'll see you all next time.